Here's a video snippet. I hope to make it short as possible, but still helpful in introducing some of the things in the lab. The write-up is called UNC, for uncertainty. One of the experiments will be swinging a tennis ball on the end of a string, and you use a simple pendulum formula to analyze this thing. And the formula comes from doing torque calculations around a pivot or however you did it in high school. But we'll revisit this also in our lectures later. The only thing I'll ask at this point is, how do we justify using a simple pendulum formula for this pendulum, with this tennis ball? That is, how must D compare with the length of the tennis ball diameter with the length of the string to justify using this guy? Just a quickie. Little analysis here to get into the standard deviation and the standard error stuff. If I made 10 measurements of the length of the string, for example, you know how to do an average. If I subtracted from X this average, normally, if you look at a bunch of answers, they'll be somewhat randomly around some average value. Now, if I subtracted away the average value, they'd be just spread around, sprinkled around zero. So their average would be zero. Well, we can prove that. Just calculate the average of X minus X bar, X average. And of course, that'll be just average X minus average X, which is zero. That won't help us in trying to think about a deviation, about a spread of anything, but if I look at the square, that's always positive, and that is useful. On page 2, I define the standard deviation. There's this factor here having to do with the fact we lose an extra degree of freedom when we're putting in an average mean and referencing everything. Or you can Google it to understand a little bit more about it, but I don't care about it because when capital N is large, that's practically 1. If I define sigma squared to be equal to this average of X minus X bar squared, and the average of that is the sum of these guys divided by n. By the way, this n and that n will cancel. Then the square root of this guy gives the formula you find in your notes. Just remember measurements and average, total number. Well, we actually like to think about the standard error, which will be this sigma divided by the square root of n. This is a famous factor that tells you can get better and better measurements if you looked at more and more of them. And I'll come back and I'll justify or give you a little better feeling for 1 to the square root of n if you haven't already done that in a statistics class. To do that, let's start with solving for g, because we could make measurements on the length of the pendulum and the period of the pendulum, and then get some measurement for g. How is the error in our measurement or our prediction for g related to the actual fundamental errors that we can figure out, or we can estimate it, we can look at for L and for T? That's what we're going to do next, and we use calculus to get a real quick understanding of it. The differential of g is just 4 pi squared. Differential of L over T squared, there's the differential L part, there's the differential of T part, familiar calculus for you. So we're going to define now to be the contribution to the uncertainty in G due to the uncertainty in L. And this to be the uncertainty contribution to G from the uncertainty in the period. Well, I'm going to define deltas, these sort of lowercase Greek deltas, to be just these terms. I'll ignore the sign, this minus sign here, because we're going to look at the squares of these things. And in fact, when I try to find the relationship between the variation of this, the standard error in this thing, and the standard error in L and in T, I'm going to end up squaring, like Pythagorean thing, a square of, or the vector squares, vector component squared. Now, to understand where in the world this comes from is what I'd like to do, rather than just lay that out for you, although you may be already familiar with it. Now, here's an example. If z equals x plus y, the error in z would be the error in x plus the error in y. Or my errors are some measurements that I have plus or minus typically. Well, the average error in Z would be the average error in X plus average error in Y, and that would be 0 because these are plus or minus on the average. And they would just cancel out. So that's not helpful. But if I square it now, I will have cross terms. And when I average over all of these guys, these cross terms are just as likely negative as positive when delta X and delta Y. They're uncorrelated. So that term averages to 0. And there's why you get delta Z squared is delta X squared plus delta Y squared. The cross terms go away. In fact, I had a little argument down below here to show that that same cross term cancellation is what ultimately gives you that 1 over the square root of n that we were talking about in the first page. If I define delta, and that is close to what standard error I was talking about, as a sum of these variations from the mean of all our measurements of all of them, the length of the pendulum or whatever, divided by n because it's an average, of course I'll just get the average of delta is 0 because the average of epsilons are 0. And now, if I square it, however, I'll get something positive, a non-zero. When I square that sum, the cross terms will go away when I average. I'll just get the squares of the individual epsilons, and if they're the same size, if they're all sigmas, that connects with what we had before, I will get n times sigma squared on the top, but n squared in the denominator from squaring this and looking at delta squared. Well, I take the square root of it. There's where this thing is related to our delta, really. It's sigma, that typical error in the individual epsilons, divided by square root of n. That's a quick way, I hope, helpful way to just sort of get a feel for 1 over the square root of n. Last page. This problem was real fast. Use F equals ma. What's the uncertainty in F? If you know the uncertainties in the mass and in acceleration. And I'll just 2 quick comments. Origin is a commercial product, commercial software you'll use to do some of your fitting, and that's like MATLAB or other things that you've been using. Once you use this thing and learn how to use it, it can be helpful for you for years. Finally, just for fun, you can ignore this, but where's Waldo in this?